Hello everyone, my name is Arshin Shabir. Today we will study the topic linear transformation of linear algebra. So let's start with the definition. If V and W are two vector spaces over same field F, then a mapping T from V to W is said to be linear transformation if T C alpha plus beta is equals to C of T alpha plus T beta, where alpha and beta belong to V and C belong to F. So this was the definition. A mapping V from V to W is said to be linear transformation if the condition T C alpha plus beta is equals to C T alpha plus T beta is satisfied, where alpha and beta belong to vector space V and C belong to the field F. Now let's see some properties of linear transformation. Let VF and WF are two vector spaces and T be a linear transformation from V to W. Then the first property is when T operate on 0, it will give 0 dash, where 0 belong to V and 0 dash belong to W. Second property is when T operate with minus alpha, it will give minus T alpha for all alpha belong to V. Third property is T alpha minus beta will give T alpha minus T beta, where alpha and beta belong to V. Our fourth property is T of C1 alpha 1 plus C2 alpha 2 and so on till Cn alpha n equals to C1 T1 alpha 1 plus C2 T2 alpha 2 still Cn Tn alpha n. So from this property we understand that the C1 is distributed to all the terms of alpha. Means T is distributed to all the C1 alpha 1 and so on. Now let's see one example. The question is, let T be the linear transformation from R square to R cube be defined as T of xy is equals to x plus y, 0, 0 is a linear map. So since T of C alpha plus beta, where alpha is equals to x1 y1 and beta is equals to x2 y2 belongs to R square and C belongs to R, can be written as T of C alpha plus beta is equals to, we will satisfy the condition here of the linear transformation, that is T C alpha plus beta is equals to C T alpha plus T beta. So we will show this here. T C of x1 y1 plus x, since T C alpha plus beta, where alpha is equals to x1 y1 and beta is equals to x2 y2 belongs to R square and C belongs to R, can be written as T C alpha plus beta. We have to show here the linear transformation property, that is T C alpha plus beta is equals to C T alpha plus T beta. So we will show it here. T C x1 y1 plus x2 y2. Now we will multiply the C here in this bracket with this bracket and this also. Cx1 plus x2 and cy1 plus y2. Now cx1 plus cy1 plus x2 plus y2 and 0, 0. Cx1 plus y1, 0, 0 plus second bracket x2 plus y2, 0, 0. Now Ct x1 y1 plus T x2 y2 equals to Ct alpha plus T beta. This is our linear transformation property is satisfied. So this is a linear transformation. Now let's see what is invertible linear transformation. Let V and W are vector spaces over F, then a linear transformation T from V to W is called an invertible if T is 1 1 and onto map. Means for invertible transformation we have to show that the transformation is 1 1 and on 2. The mapping is 1 1 and on 2. Let's take an example. Let T be a linear transformation on V3R defined by T of ABC equals to 3A, A minus B, 2A plus B plus C. For all ABC belong to V3R. Now we have to prove that T is invertible. Means this transformation is invertible transformation. So for proving invertible, we have to show that it is 1 1 and on 2, which is the condition of linear transformation, invertible linear transformation. Let alpha equals to A1, B1, C1 belongs to V3R and beta equals to A2, B2, C2 which belongs to V3R. So now let T alpha is equals to T beta. T of A1, B1 and C1 equals to T A2, B2, C2. Now we will put the value of, not value, put the condition of T of A, B, C, that is 3A, 3A1, A1 minus B1, 2A1 plus B1 plus C1, which will be equal to 3A2, A2 minus B2, 2A2 plus B2 plus C2. Now we will see from this 3A1 equals to 3A2, A1 and A1, 3 will be cancelled out both the sides, so A1 will be equal to A2. Similarly, B1 equals to B2 and C1 will be equals to C2. So this was the condition of 1 1. Now since T is linear transformation on a finite dimensional vector space V3R whose dimension is 3, so T must be on 2, hence it is invertible. We have proved that the transformation is 1 1 also and all 2 also. Hence we can say that a linear transformation is invertible. Now we will see the range of linear transformation and null space of transformation. So what is range? Let UF and VF be two vector spaces and let T be a linear transformation from U into V. Then the image or range of T is denoted by R of T. R of T is the set of all vectors beta which belongs to V such that T of alpha equals to beta for some alpha belongs to U. RT is equals to set beta belongs to V and T alpha equals to beta for some value alpha belongs to U. This is the range of linear transformation. What is null space of linear transformation? Let T, the transformation from U to V, be a linear transformation where UF and VF are vector spaces. Then the set of all vectors alpha of U such that T alpha equals to 0 is known as null space of T. It is denoted by N of T or K of T. We can K is here kernel. We can say null space or kernel also, and also known as kernel of T. That is N of T, that is null of T equals to alpha belongs to V, that is T alpha equals to 0. So this is the null space of transformation. Thank you.